So in the last lecture, we studied the hybrid method, Levenberg-Marquardt method, and in this lecture, we will see how it is used in solving systems of nonlinear equations. And in the context, we will cover nonlinear equations topic properly. Is I mean, even what does not involve typical optimization technique, because nonlinear equation solving is something which is very important for people who uh, do optimization. Okay, so this topic, solution of nonlinear equations, is a numerical method area which is very closely connected to optimization. So we'll first consider a single equation, something that you actually know to an extent, and then we will go to systems of equations. So how does equation solving get connected to optimization? It is through the first order condition, because first order condition is typically an equation. First order condition of optimization is typically an equation, which is in general nonlinear equation. And so in solving optimization problems, solution of nonlinear equation appears into picture. And then we will see how solution of nonlinear equations also gets benefited by the methods of optimization that have been developed. So the two problems help each other and also get helped by each other. So as users and as providers. Okay. So root finding of a single equation in a single unknown fx, ordinary single equation. This is a building block of problems in many areas. In whichever area you work, now and then you get equations which are nonlinear. Single equations you just get almost anywhere. And when you have the problem of solving a single equation or finding roots of a scalar function like this. So for a function, it is a root or 0. And for the corresponding equation, that function equal to 0, that is an equation for which you find solution. So root of a function, solution of an equation. So only polynomial equations up to degree 4 you can solve analytically. There also the calculations are very involved, but you can do it analytically in the sense that you do not have to resort to iterations. And by a constant number of calculations, you can find all the roots, real or complex. Now, beyond degree 4, till the end, you cannot go analytically. But still, if it is polynomial equation of whatever degree, whether you can find the solutions finally or not without iterations, you can do a lot in terms of pre-processing so that systematically you can find all the solutions, real as well as complex. But in general, for nonlinear equations, for numerical algorithms, methods are iterative and they typically try to find a single solution. They're also real. Okay. Starting from another point in another run, you may find another root or maybe the same root all over again. I mean, all these things can happen. Now, some luxury which you don't have in the case of multidimensional problems, but for a single variable, for an equation, you can do bracketing. That is, you can work out an interval in which you are sure to find a root. So that basically depends on continuity of the function. Because of continuity, you can say that if at 2 points the function has opposite signs, then in between it must cross a 0. Okay, so that is bracket. And make note that earlier we did bracketing for optimization, where we were looking for high, low, high pattern. For equation solving, bracketing means something else. It is negative on one side, positive on the other. Okay. Then bisection method is the simplest method to solve a single equation. So whatever bracket interval you have got, the midpoint of that, you try to see the sign of the function at that point, a plus b by 2. And depending upon its sign, you replace either a or b with this. Thereby, at every step, you basically bisect the interval. So many times if you bisect the interval, finally you have got the solution trapped to a very small region. Okay, and that may be all right for your tolerance level. So that is the simplest and most fundamental method to solve a single equation. For a system, you will not have this whole thing. No bisection, no bracketing even. Now, what are the other methods? Not so simple, not so basic, but hopefully more efficient. So the most well-known method is Newton-Raphson method. The theoretical basis of the method is essentially first order truncated Taylor series. And if you want this to be zero, that is from a given x, if you want to find out delta x so that at x plus delta x, the function is zero, then basically you equate this side to zero and solve it. Find out delta x, that will be minus f by f prime, and then that you add to the current x and you get the Newton-Raphson iteration formula, right? The geometric sense of this formula is basically to draw a tangent at the current point xk fxk, and wherever that tangent crosses x-axis, to take that as the next iterate. Okay, its local convergence property is good, as always happens with Newton kind of methods. Essentially, this is directly linked to the Newton's method for optimization, and global convergence typically is not guaranteed, but if you find that this condition is satisfied, then you expect convergence. Okay, and if there is an interval in which this is satisfied and you have taken your initial point within that interval, then it will converge. Most of the time that is not possible, and catastrophic outcome may come out if this derivative turns out to be very small. And that means the tangent is almost horizontal. Okay, so if the tangent is almost horizontal, then it will cut the x-axis at a far away point. Delta x will be huge, and then this basic truncation of the Taylor series at first order will not be valid. So that is why this may be catastrophic. Okay, so if used Newton-Raphson method, it should be provided with some safety net so that such things don't happen. So you can engineer several kinds of safety nets, some based on very common sense. Now the next method is secant method. Its theoretical basis is basically to replace the derivative in Newton's iteration with a finite difference estimate over 2 points. So that is why function value difference divided by variable value difference. So it has got upside down because the derivative was in the denominator. Given like this, its geometric sense is basically to join a chord means secant, join a secant between 2 points, k minus 1 and k. And wherever that chord cuts the x-axis, take that as the next iterate. And then out of the two old points, drop one of them, retain the other, and you have the new point. With these 2 points, you go to the next iteration. Okay. So here also catastrophic outcome may come if these two are equal or very close. Okay. Then that chord is horizontal and therefore you will cut very far away. Okay. However, you can stop it if you insist that out of these 2 points, one should be one should have positive function value, the other should have negative function value. If you insist on that, if you ensure that, then the method that you have is method of false position, which is also second method. Okay, because that also operates based on second, but that is a special case. And this is the advised way of using second method, because if you have 2 points to operate with, you have to operate with 2 points, then why not start with a bracket and use those 2 points and go on with the iterations. And in this case, convergence is guaranteed. There is no question of any catastrophic outcome because all the time bracketing is maintained. So in that case, in order to maintain the bracket, what you will do for the next iteration, you retain those 2 points which are on opposite sides of the 0. And in this case, the denominator cannot be 0 because one of them is positive, the other is negative. So the difference cannot be 0. Difference cannot be very small either. Okay. So that is why regular falsy, this method of false position, or in other words, second method with the bracket, maintenance of the bracket, is convergent. There is no problem there. However, there are better methods. And currently, Brent method is considered the best to solve a single scalar equation. It has actually got contributions from several others. The full name of this is Van Weingarten Decker Brent. So before Brent, the person who made contributions in this method is Decker. Okay. So Brent method is considered an improvement over Decker's method. And there is a little background to the method. Like Newton's method, second method, there are other interpolation based methods also to solve a single equation. So there was a quadratic interpolation method or quadratic estimation method, so which gets seeded with not 2 points but 3 points and doesn't use derivative. Okay, I mean doesn't use derivative value concept, it can use. So seeded with 3 points x0, x1, x2, it can develop a quadratic model of the function and then say that locally I will take this quadratic model as the function itself and solve this equal to 0, and based on that get the new point. After getting the new point, out of the 3 old points, discard 1, retain 2 old points, and this new, go to the next iteration. There is a little problem here. What if this quadratic turns out to have only complex solutions? Then you are stuck. Typically, it does not have if the points are close by, but it might have in principle. Besides, in any case, even if the solutions are real, most of the time there will be 2 real solutions. And you will have the additional headache of choosing between the 2 real solutions. There is an alternative which is inverse quadratic interpolation. Okay, so in quadratic interpolation, you interpolate y as a quadratic function of x. Here you interpolate x as a quadratic function of y, a plus by plus cy square, and then say here we will now solve f bar equal to 0. This model here y equal to 0. The moment you put y equal to 0, this will go off, this will go off, x will turn out to be a. Okay, and here there is no question of it becoming complex. There is no question of 2 options or whatever, 2 solutions, a single solution. So basically, in the inverse quadratic interpolation, the quadratic that you get in that b and c you don't need to evaluate. Basically, b and c you have to eliminate to get A. Get hold of A, and that is the next X. So Brent method, which we are going to talk about, this maintains a bracket across iterations all the time. It starts with 3 points. Basically, bracket is already there, so another point you take. And for every iteration, for X new, it works out two possible candidates. One based on inverse quadratic interpolation, another based on bisection. Both are sure actually. However, it chooses the better one based on some appropriate conditions. In fact, you can work out your own favorite conditions. The textbook method works out a kind of conditions based on some considerations. You can take that, or you can even work out your own method, your own conditions based on which you choose either the bisection estimate or the inverse quadratic interpolation estimate. So one of the two. After getting X new, you drop one of the old points in such a way that out of the remaining 3 points, two old, one new, some are on this side of 0, some are on that side of 0. Okay? So this is, safe as well as efficient method to solve a single equation. Now we go to system of equations. And for that, the basic method is Newton's method, which is basically the generalization of Newton-Raphson method to multi-dimensions. To solve a system of n equations in n variables, again, we use the first order truncated Taylor series like this, and xk we have in hand. We want a suitable delta x so that at the corrected changed point, h will be 0. That means this should be 0. From here, we can solve for delta x, which will be minus j inverse h. So minus j inverse h, that delta x, we add to the current point xk, we get the next point. This is the iteration formula. Okay. So for termination, you can use the condition that this is very small, or you can use the formula. You can terminate a condition that this is very small. Okay, which is then either the norm of change in x, correct value of x you don't know, so you cannot say correct the error from the correct value of x. So all that you can say is the update value. Okay, delta x. Either this is very small, or you can say hx norm is very small. As I told you, it is visible as a generalization of the Newton-Raphson iteration formula for a single equation. And I will remind you that this is also the iteration which was used earlier to solve the first order condition for optimization problem, right? So this actually used this iteration formula in Newton's method. However, there the advantage was that in place of h, we had a function which was a gradient of something, gradient of a scalar function, and therefore its derivative turned out to be Hessian in place of this Jacobian, and the Hessian was symmetric. That was one difference. Okay. Now, local convergence is quadratic as expected from a Newton's method, but it may not work because it does not have global convergence. No guarantee of function value decreasing. Okay, that is h norm decreasing. So, and Jacobian may be singular, you don't know, and then you will be in trouble. However, most of the cases, many cases it works, but you don't know in which case it will work. So for this example, you see, this is the Jacobian. So you start from x naught, say origin, where half h norm square is 50, and that you can see. At 0, 0, h will be 8, 6. So 8 square plus 6 square is 100. Okay, half of that is 50. It's visible. In this case, the process actually converged in 6 iterations to this point, which is a valid solution, where this E value is this very small. I mean, even after that, one iteration gives you exactly 0. I mean, after this, in the 6th iteration, after the 6th iteration, after the decimal point, so many zeros are there that you cannot differentiate it from 0. Even this cannot be differentiated from 0 much. Okay. Now here also, but notice the changes x1 x1 at x2 at x3 at x4 at x5 at x6. Exk is continuously decreasing. Okay, h norm. But from x0 to x1, see, from 50 to 84.4. So the first step was actually a bad step. Okay, but after that it recovered. So Newton's method sometimes, even after taking one or two intermediate uphill steps, later may come down. Sometimes it does not come down. Okay, so there is no guarantee. So in this case, it worked because we were lucky. This system was good. Okay, at least it was not too bad. And for that, 0, 0 origin was not too bad a starting point. If the system of equations and initial point together are quite bad, then it could have taken us anywhere. Okay. So I suggest you to take the task of solving this system as an exercise by Newton's method and also by methods that we are going to discuss afterwards. And from the origin, 0, 0, and from some other points also. And see how it may happen that starting from some points, the method works, and starting from some other point, it does not work. Or it works and goes to another solution. Systems of nonlinear equations may have more solutions. For that matter, may not have solutions also. Anyway, so one method we learned, Newton-Raphson method, which is the most basic one. Now, what about second method? So for a single variable equation solving problem, the second method avoided computing the derivative by using the estimate of derivative based on this. Derivative into delta x equal to delta f between 2 points. Can we do such a thing in multi-dimensions also, higher dimensions also? The problem is that the Jacobian here, in place of f prime, we have Jacobian, okay, which is a matrix. And that does not get determined by one equation of this type. Based on one chord from xk to xk plus 1, within 2 points, you have one delta x and one delta h. With that, you cannot determine j completely. And that's a problem. So Broyden solves it in a very ingenious manner. This indeterminacy, that j does not get determined completely from this equation, Broyden says, okay, fine. So at the initial point, you calculate the Jacobian faithfully. Okay. And after that, based on the step from x0 to x1, from x1 to x2, based on the step delta s x and corresponding delta h, you work out a correction of this form. A correction of this form where u, k, and vk are vectors, single column, okay, is called rank 1 correction. Because this is a matrix, this is a matrix, this whole thing is a matrix, but this matrix AK is scalar. Okay. UK is a vector, VK is a vector. So UK is a column vector, VK transpose is a row vector. When you multiply that, you get a matrix of this kind of a size n by n. But its rank is 1. That means its information content is very little. You can see that an n by n matrix you are actually capable to represent with two vectors and a scalar. For the matter, just two vectors you can say, because this scalar you can include either in this or in that. Okay. Now the question is, what AK, UK, VK we should use to get correct or useful update for the Jacobian, okay, which serves our purpose. Now, Initially, J0, which was computed, the correct computed Jacobian at x0, actually did not map delta x to delta h correctly like this, because we started with j times, okay, we started with, on this side, we started with just minus hx. That means 0 minus hx. Now 0 is hx star. So here we actually gave the delta h corresponding to fx star minus fx0. So here it should have come x star minus x0, okay, delta x. So we started from x0, so we should have come to x star, but that we did not come. We came to x1, where h was not 0. The reason is that Jacobian is supposed to map infinitesimal change in x to corresponding change in h. We gave it the task of getting the finite change, and so it could not do it. Of course, it tried, okay, but it could not do it because that was beyond its power. And also note that this jk plus 1, that is at every iteration, at the end of every iteration, for the next iteration, the Jacobian that we work out by an update of this type, since we are going to work it out on this kind of an update, xk to xk plus 1. So basically, even though we are writing it as jk plus 1, it will not be the Jacobian, even we don't expect it to be the Jacobian at xk plus 1. We are basically working out or trying to work out the Jacobian value at a point x bar, which is on the chord from xk to xk plus 1, because mean value theorem says that between xk and xk plus delta x, on that line segment, we have some point where the derivative stands in the place of the coefficient matrix for mapping the change. Okay, fine. We try to get that because for that we have information, and that we will use for the next iteration. So, how to find this? So basically, to find this update, we need to demand some properties, impose that, get corresponding equations from which this can be worked out. So what properties to try to demand? Say jk did not map delta xk correctly. That is, jk inverse did not map delta fk correctly, delta hk correctly. But now we try to get a jk plus 1 through a proper update of this kind, so that this fellow does map the change correctly. This is one thing. And we said that one such equation is not good enough. So what else we use? We say that on all the vectors delta xk, whatever was the effect of jk, let jk plus 1 also have the same effect. So let jk plus 1 map all the orthogonal vectors orthogonal to this direction exactly as jk would have mapped. Okay. So put these two conditions and you will find that the update gets determined. So first condition, jk plus 1 delta x is correctly delta hk. Okay. So when you say that, basically you get this. This is the form of the update. Jk plus 1 times delta xk is this. Now when you multiply it out, then and take jk delta xk on the other side of the equality, then you have got delta hk minus jk times delta xk, and that leaves the rest, ak uk vk transpose delta x. Now matrix multiplication is associative, so vk transpose delta x you can put like this, and this is a scalar. Now this is a scalar times this vector is equal to this vector. So ak uk will be this thing divided by this scalar. In fact, AK also you could have taken on that side, but not needed. You keep AK, UK together. So the whole thing you have got together. This. Now AK, UK you have determined. All that you need now is VK. For that, you use the second condition. Other vectors orthogonal to delta xk. So on that, jk and jk plus 1 should map in the same manner. So you say that any vector that is perpendicular, that is orthogonal to delta xk, this, for that, the effect of jk plus 1 and jk should be same. And in place of jk plus 1, now we write this, but here ak uk, we put this thing. Okay, this thing. And then when you say these two are equal, then on this side jkwk will get cancelled with this jkwk. And what remains is this thing, that is what we know as akuk, into this scalar vk transpose wk. And that is 0 because jkwk cancels out. This is the only term. And now this is not 0. At convergence, this will be 0 because then this would be correctly mapped. But before convergence, as long as this is not 0, vk transpose wk has to be 0. And that means that wk and vk are orthogonal. But wk and delta xk were also orthogonal. So vk is along delta xk. Along is good enough because any scalar multiple of delta xk, if you put, that will come here as well as here, and that scalar will get cancelled out. So as good as delta xk. So just put vk equal to delta xk. And then you have got the update completely. Jk plus this thing, where in place of vk you put delta xk here also. So this turns out to be the Broyden update. The denominator delta xk transpose delta xk can be written like this easily. Okay. So this updated matrix replaces the computed Jacobian for subsequent iterations. So after the initial point, we never compute the Jacobian again in Broyden's method. Rest of it is just like Newton's method. For that example, for which I showed you the results for Newton's method, Broyden's method also converged, not in 6 iterations, but 9 iterations. Okay. And if you trace the Jacobian, the updated Jacobian across iterations, and separately compute the Jacobian correctly and compare, you will find that in the initial steps, slowly the correct Jacobian gets a little damaged. Some errors crop up. But towards the later iterations, near convergence, the Jacobian, updated Jacobian gets corrected. Okay. Now, in place of 6 iterations, here 9 iterations are required. I mean, 9 iterations it took. And this is quite all right because in many problems with complicated function, complicated Jacobian calculation, multi-dimensions, maybe not just 2. This example was in 2 dimensions with something like 40 dimensions. 50% increase in number of iterations is actually reasonably good if that frees you from Jacobian computation in every iteration, because every Jacobian means n squared derivatives. Okay, and one derivative itself means one more function evaluation. Okay, so like Newton's method, Broyden's method also does not have global convergence because nothing was done to handle ill conditioning. Okay, exk may not decrease in some iterations, and it may keep on increasing and go unbounded up, which will be very sad. So such things can happen in Broyden's method also. A modified Newton's method also has been suggested, that don't take the full Newton step, but conduct a line search. which has some safety value compared to Newton's method. But still, if the Jacobian itself is ill conditioned, then what can you do? Okay. So the original problem remains. One basically different approach to solve a system of nonlinear equations is by formulate it as an optimization problem. And this turns out to be the most sophisticated and professional approach to solve an equation system like this equal to 0. Okay. So first reformulate it as an optimization problem. It should be hx equal to 0 because it is equation system. Okay. So to formulate it as an optimization problem, you first need to define a scalar function like this, which we have been talking about for some time, for which the gradient is this, which also we have talked about, and a Hessian is this, which gets approximated by J transpose J without bothering to compute the Hessian. Okay. Here, this cannot have a negative eigenvalue. Okay. Even in the worst case, its eigenvalue is the worst eigenvalue, maybe 0. And that also in very rare cases. Okay, we will talk about when. The actual problem with this formulation is something different. This function may have several minima, and some of them may be local minimum, some of them may be global minimum. Global minimum will have a value 0. And only when this is 0, you have got a solution of the equation system. Because only when this is 0, you know that h1, h2, h3, h4 are all individually 0. And that is what you wanted actually. So just a minimum will not do. So it may happen that the method converges because the method has been said that you try to optimize this function. Okay. And it has optimized it. And in the local neighborhood, everywhere the function value is higher, at this point, the function value is 1.3. But that is not okay in this case, because in this case, minimization of this was not the original problem. Original problem was to solve the system of equations to get all zeros. So only only that x star is acceptable where the function value is 0. So after convergence, it has to be checked. So for this optimization problem, you can use many methods, any optimization method. But as we have earlier discussed in the last lecture, Leavenworth-Marquardt method fits the bill best. And this handles all the ill conditioning related issues properly, because the only issue of possible singularity of the representative Hessian is remedied now by the routine enrichment of this. Okay? And this enrichment version is immune to all situations except, I mean, even if J transpose J is singular, this is unlikely to be. Okay. And this also can be singular only in that condition when one column of the matrix is positive. If it is differential, then then is positive gradient. However, for each solving, we use this. Like that, but this really not like that, so we can use this. But this itself, if I have any routine and everything, this positive is situation. Now this is only like this. Even while children granted transfer situation, you want to start with one, identify one also what it works. This is easier. After convergence, you must check this. Unless it is 0, it will be a minimum of the function x, but not the solution of the original problem, the root finding problem. It is a problem. So this is the must check. Now the second version of the normal method. But if you read the side, it works. Because I tried it for the same system for the business methods. And we get one it's from the same word. It is something I use in the relations. Sometimes, but finally, all the things get settled. So you can use the word in the also. It is equations. the allegation of irrational method is called method.